Welcome to this talk on design and implementation of a convolutional neural network on an edge computing smartphone. Our use case in this scenario was human activity recognition from wearable devices. If I begin with what motivated our research, it would be we wanted to bring deep learning models to mobile devices such as smartphones and wearables so that we can have on-device intelligence. Today, many of the mobile and embedded devices come with high-performance hardware acceleration, which makes it feasible to do powerful on-device computations. In this paper, we investigate the resource requirements for the deployment of deep learning models on wearable class smartphone hardware. Our study is motivated by the fact that wearable devices are becoming increasingly popular for their use in healthcare and their on-body nature. We will also take you through the necessary steps that has to be taken before we train a model and implement it on an edge device to do inferences on new data. As we start implementing the app, first thing we need the core TensorFlow library written in C++. We need functions such as load model, get predictions. We must have a pre-trained model file and label for the classifications. As we train a model, as you can see in the model fit function where we fit the model with training data and training labels, what we do is we save the model. In this case, as it is a human activity recognition app, we save it as an optimized H5 file, and we then need to serialize it so that it can be saved in an edge level device. The file formats could be either protobuffer or TF-Lite. The next thing we do is like the H5 file has to be converted using functions TF-Lite, TFL converter, and we write it as a TensorFlow model file with a specific name and extension. If we now discuss what was placed inside the optimized HAR app, so we had to start with 6-channel inertial sensor time series. We needed to do some pre-processing such as segmentation. We chunked the activity windows in 128 consecutive samples to get a sense of what activity the person was doing. We did scaling and normalization. As you can see, accelerometer and gyroscope comes with 2 different measurement units. It needed to be scaled between the range of 0 to 1. Once we have the activity windows segmented with their associated class levels, in this case we have to label 5 different activity classes such as walking on level surface, walk upstairs, downstairs, sedentary activities such as stand set, and sleep activity. Once the data is ready with the training windows and the training labels, we pass it through the convolutional neural network. So in the network, depending on how many layers of convolution we have used, the finer detail from the time series will be extracted. So in case if we say we are passing the sensor data through 12 convolutional filters, 12 different copies of each channel will be processed by n different filters to find out different features from the time series. Then we applied max pooling to look into a smaller chunk of the convolutional layer, find out all the features. The next stage is to pass it through a classifier to group them together. So we have used a 3-layer dense neural network, fully connected classifier to do our classification. We have also presented our observation of kernel size, number of layers in the paper. One interesting observation was if the filters are looking for different types of features in the time series, after a specific size of the kernel, the observation of the features become blur or saturated. We have also tried dropout and batch normalization technique so that the model is more consistent. Suppose a generic CNN has some spikes, dips, or inconsistency in model performance. A model with dropout and batch normalization seem to have less variance in its performance over multiple iterations. For our 5-class activity classification scenario, the overall accuracy for the model was about 96.4%. As we trained the model, the next stage was to minimize its size or reduce the memory requirements of the model. So we have applied quantization. The weight values, which were 32-bit float numbers, were converted into unit 8 numbers. Weight quantization reduces the number of weights into discrete chunks. Quantization helps the memory footprint of the model to reduce. Suppose if for a convolutional neural network with a 4-layer neural network we had 72 weights, and then max pooling operations, each of these operations consume an amount of memory in the model. Converting a 32-bit floating point model to an 8-bit fixed point quantized model, we achieve a reduction in the size. As our model is ready, we are ready to place it inside our Android app. We developed it with Android Studio. Both protobuffer and TensorFlow extension of the safe model works with it. Currently classified 5 different ambulatory activities using 6-axis accelerometer and gyroscope data. It can be extended to identify more complex activities, but for now, as it is a proof of concept situation, we limited ourselves with the daily life activities. To be noted, we are not doing any training on the smartphone. We are on the testing, the inference stage. The power consumption of the app is pretty low. When measured, it was about 39.30 milliwatts. If we now go to the Android app to see where we placed the models and the other things are set, we placed our optimized models inside assets, the buttons to show the probability of what activity the user is doing. We will set those things in our layout file in activity main. The probability will be shown based on the model's output. And in those files, the results are the probabilities that the model is suggesting. So we use the TensorFlow inference interface to do those predictions. So this was it for our Android app development. TensorFlow Lite is now available for microcontrollers and other chips. So if we conclude it now, the proposed model, the CNN model, we empirically analyzed it for the memory requirement and execution time, and we observed that almost all size and execution time reduction in our optimized model were mostly due to weight quantization, and proposed model has been validated and successfully implemented on a Samsung A5 smartphone. Results of this study would be useful for making smart wearables and devices which can be standalone or will give us on-device intelligence, potentially improving the user's privacy.